let's get started. This is the first part of the talk, bifurcating minimal surfaces with symmetries. As a reminder, this is a talk in 4 parts. The first part is symmetry reduction for minimal hypersurfaces, and we'll be following closely the work of Xiang and Lawson. Okay, so here's the problem I want to discuss in this part of the talk. Suppose G is a Lie group acting isometrically on a Riemannian manifold MG, and we wish to find G invariant minimal hypersurfaces sigma in our manifold M. So sigma here will be some hypersurface in M, but I want it to be made of orbits. So these blue curves perhaps denote G orbits. And since they are G orbits, these correspond to points in the orbit space M on G. So we would like to find minimal surfaces in this way. Okay, so the setup here is the following. Let denote by pi the quotient map, and by MPR, the principal part of our manifold with respect to this action. So that's the union of principal orbits. Recall that the union of principal orbits is an open dense subset. It's also connected. And restricted to this open dense subset of the principal points, the projection map is actually a Riemannian submersion. So there is a Riemannian metric here on the principal part of the quotient, such that this projection, this quotient map, is actually a Riemannian submersion. We can then look at the volume function of principal orbits, which I'm denoting here by this function there. And this function is smooth, and it extends to a continuous function on the whole orbit space. So the continuous extension, I'm denoting it by V, and that's a function, a real valued function on the whole orbit space. If the orbit space happens to have boundary, for example, in this picture here, the boundary is non-empty, then the volume, this volume function is 0 along that boundary. That doesn't mean that the boundary corresponds to fixed points or orbits of 0 volume. It just means that they have 0 volume in the dimension of the principal orbits, right? So what it means is that the orbits corresponding here to the boundary, they are lower dimensional orbits. All right. So throughout the talk, I'll denote by omega the Riemannian manifold obtained by looking at the principal part of this quotient and equipping it with this conformal metric. So here, G check is the metric that makes that a Riemannian submersion. And then I insert this conformal factor, which is an appropriate power of the volume function that we were just talking about. In this power, K is this number here. So the dimension of the principal part, which I guess in this picture is denoted here by this gray area. So this is the principal part, minus 1. All right. So here's the theorem of Xiang and Lawson. So we want to characterize minimal hypersurfaces which are G invariant. And the characterization is actually quite beautiful. It says that you are minimal upstairs if and only if you're minimal downstairs. Okay, so a hypersurface like this made of orbits is minimal in M if and only if the image down here, maybe I should denote there, there's a sigma principal part mod G, if and only if that image is minimal in the quotient when we equip the quotient with this conformal metric. Okay, so omega here, remember, is with the conformal metric. So it's a very simple proof. So let's just go over this argument. So we begin by observing that since sigma is G invariant, it's the union of orbits, right? So it's the union of all pre-images. Let's say X is a point in the image in the quotient. So we take all the pre-images. These are all the orbits. If we take the union of that, we get the whole sigma. And of course, the volume of sigma can be computed as an integral. So using Frobenius theorem, really, I can write this as the integral of the volume of each of these orbits. right? So remember, Vx is the volume of these principal orbits. Now, I can push this V into the measure, right? I can push this into dx by changing the metric, making it a conformal metric. And that's exactly the reason why we have the conformal factor there. So if you look at the volume form of the metric V to the power 2 over K times G check, then this conformal factor comes out with a certain power that is exactly K over 2, since K is the dimension of sigma PR mod G. And so I get exactly V. So perhaps that's the observation I should have made up here. This is exactly the dimension of the image of a hypersurface. Okay, if sigma is a hypersurface in M, K is the dimension of its image in the quotient. Okay, so that this equality here works out. All right, and that's the volume of this image downstairs in the conformal metric. Great, so now we're really set up to finish the proof, because being minimal, so this of course means you're a minimal surface upstairs, minimal, let me say sigma minimal in M, means that you're critical for all variations, right? So you're a stationary point for the volume functional with respect to every variation. That means that, that in turn is equivalent to being critical for all G invariant variations. So if I look at, let me write down the same thing here, but now for all variations sigma t, which are G invariant, if I look at G invariant variations, it's a subset of variations, it actually captures criticality with respect to all variations by something, for example, that goes by the name of Palais' symmetric criticality principle. Symmetric criticality principle. It just means you can, it comes from the fact that you can take an integral of this variation and make it G invariant. So the restriction to G invariant variations is a natural constraint. All right, but as we saw, this volume function here is exactly equal to the volume downstairs, right? So if I apply this equality to all of these variations, sigma t, that's exactly being critical for the volume function in omega. So being critical when we take variations of the principal part mod G. So let me maybe denote that like that. So this is equal to 0 for all variations indexed by t here downstairs. And this is precisely what it means to be minimal in omega. So maybe sigma mod G minimal in omega. That's this other side of the equivalence. So that shows that these two things here are precisely equivalent. Okay, so in particular, let's observe that if the dimension of the quotient is 2, those are called actions of cohomogeneity 2, then being minimal in a two-dimensional ambient, being a minimal hypersurface of a two-dimensional ambient means precisely being a geodesic there, right? So a curve is a minimal hypersurface of a two-manifold if and only if it's a geodesic. So we're looking for geodesics. And these geodesics could live inside. Maybe they even have like some self-intersection, right? Or they could touch the boundary. Or they could look like that. And if we are looking for a closed submanifold upstairs, well, then we are looking for closed geodesics. Now, if there's no boundary, then in this picture, we can imagine maybe this red region here is the boundary. If there's no boundary, imagine that this is all identified to a point, say, then this is the same thing as asking for closed geodesics. But if there is boundary, then the geodesic could either be closed, and then the preimage is again a closed submanifold, or it could be free boundary. It could meet the boundary at an orthogonal angle, at a 90 degrees angle. And in that case, we also get a smooth closed submanifold upstairs. Okay. Now, of course, if we want the submanifold upstairs to be embedded, we need the quotient to also be embedded. That's actually an equivalence. Okay. So the problem of looking for closed embedded minimal hypersurfaces in a manifold with an isometric group action corresponds to that of, if the action is cohomogeneity 2, corresponds to that of looking for closed geodesics or free boundary geodesics, which don't self-intersect. All right, so here are some applications of this idea. There's this classical problem proposed by Chern in analogy with the Bernstein problem. And if you take the unit ground sphere, of course, every equator, every intersection with a hyperplane through the origin defines a totally geodesic minimal subsphere, right? In particular, they're minimal. And the question is, are these all of the minimal spheres in a round sphere? So is it true that every embedded minimal Sn-1 inside the n-dimensional unit round sphere is every such submanifold planar? Meaning, is it congruent to an equator, right? Such as the red equators drawn here. So the answer is affirmative in dimension 3, and that's a well-known theorem of Almgren. But actually, even starting at 4, the answer switches to no. That was discovered by Xiang in the 80s. So it's in the seminal work of Xiang, it was established that this is no for n equal to 4, 5, 6, 7, 8, and now you skip 9, and you go to 10, 12, 14, and there's a few other dimensions that have been filled in here. But anyways, there's an abundance of dimensions, more importantly, starting at 4, that in which equators are not the only minimal embeddings of spheres. And the way that these non-equatorial minimal spheres are found is exactly using some group action, some group that acts by cohomogeneity 2 on our sphere. Here the quotient will be something of dimension 2. And then you look for geodesics that are, for example, free boundary geodesics, since this guy will have boundary. And some of them will correspond to equators, right? So some of them will correspond to these trivial solutions. But if you can produce some that are not, well, then you found some minimal spheres which are not equatorial. That's exactly what Xiang did. Okay. The other application I want to discuss of this idea, and that's where we'll spend a good amount of time in the last couple parts of the talk, is related to this problem of Yau. So by some analogies with what happens with geodesics in two-dimensional spheres, Yau proposed this question of whether the only minimal spheres in this ellipsoid, so this is a three-dimensional ellipsoid sitting in R4, semi-axis A, B, C, D, whether they are necessarily these 4, well, in the picture there's only 3 since I'm dropping dimension by 1, if there's only these 4 planar minimal spheres, namely the intersections with the 4 hyperplanes orthogonal to the 4 axes in R4. Okay, so we'll denote these by pi I. So pi I is the intersection of the ellipsoid with the hyperplane xi equal to 0. Of course, again, these are totally geodesic. So maybe I'll indicate here. These are totally geodesic since they are the fixed point set of a reflection, and in particular minimal. And the question is, are there any other ones, right? So Haselhofer and Katover proved that indeed there's at least one non-planar minimal 2 sphere if one of the semi-axes is large enough compared to the other ones. So let's imagine, for example, here this distance is A. So that's the first semi-axis. If we fix the other semi-axis B, C, D, and so on, then if A is large enough, using min-max theory and min-curvature flow, they were able to produce a non-planar minimal sphere. Then in joint work with Paolo Piccione, last year, we were able to find arbitrarily many non-planar solutions. And of course, here, arbitrarily many up to congruences. So they're not just isometric images of one another under some rigid motion, if A is large enough. And if we have at least two of the semi-axis coinciding. So if either B is equal to C or C is equal to D, then we're able to produce as many non-planar minimal spheres embedded in these elongated ellipsoids, as many as you want. So in this result here, no further symmetry assumption is needed. They do not need B equals C or C equals D, but they only produce one solution. We have a stronger set of hypotheses, but we produce arbitrarily many solutions. More precisely, the number of solutions goes to infinity as A goes to infinity. And I'll discuss this in detail in the third part of the talk, actually. So this will be discussed in part 3 of the talk. Okay, before I finish this first part, I'll just mention some other applications of this symmetry reduction principle. They appear since the 80s. There's been a lot of use of these ideas, for example, in work of Alencar and Wang to find non-planar minimal hypersurfaces in Rn. So again, it's somewhat related to Bernstein problem, but these are not, they're not graphs, right? They skip some part of space. Some of them actually meet the unit sphere orthogonally and produce minimal free boundary surfaces in the unit ball. So there's some work on that by Frieden, Gullion, McGrath in 2017 and Ziffert-Wuzik last year. And there's some really recent work of Carlotto Schulz, which prove the existence of embedded minimal 3 tori in the 4 sphere using these ideas as well. One main difference between these applications, these 3 applications, as well as Chern's problem solved by Xiang and the question on ellipsoids, is that on the ellipsoids, the quotient has no killing fields. There are no further isometries after you take the quotient. While on these other cases, since it's a round sphere here or Euclidean space there are further isometries. So this will come into play a little bit in the comparison between the problems I'll discuss in the last 2 parts of the talk. All right.